Now, this is again another important aspect that we need to discuss in shear. Now, how we talked about what is the shear span to depth ratio. So we looked at the relationship between normal stress and shear stress, right? So F normal stress by tau is proportional to A by D. So if I'm taking a section which is close to the midspan for a simply supported beam, then and I'm considering that effect, I'm going to have higher A, which is higher shear span, right? So higher the shear span means my bending effects are going to be large. So if this value is high, then your numerator has to be high, right? So your bending or normal stress effect is going to be high. So that's what we said. So in this figure, we are looking at what is the effect of, let's say, if I'm how that failure is going to happen, and this failure in shear actually depends upon how the beam is going to behave, whether it is in bending or in arch. Whether it is going to behave in bending or arch action again depends upon how you load the beam. Okay, now this is a scenario. All the beams are having constant depth of, let's say, D. Okay, all of them have constant depth of D. Okay, now only I'm saying is the way I'm loading, length is also remaining same. The way I'm going to load is going to be different. The first beam is having a higher A, or in other words, higher A by D. A by D is very high. Okay, here A by D ratio, let's say, higher than 6 in this case. Here A by D ratio is between 2.5 and 6. Okay, here A by D ratio is less than 2.5. So these are the three scenarios that we are going to look at and see what is going to happen to the failure. Okay, so let's say if I'm my A by D ratio, so I'm looking at what happens, what I'm plotting now. Let's focus only on this top figure here. Okay, for each section, depending upon the reinforcement, my flexural capacity can be calculated. So let's say I'm giving the reinforcement along the length of the beam. You do your moment curvature analysis or your IS 456 calculation. This will be given. Let's say that this beam is having a constant tension reinforcement. So at every section, it is going to have a constant flexural capacity. Okay, so that let's keep that as what is the capacity of the beam as a red color. Okay, now what we are plotting here is this is the load at which it is going to fail. Okay, so this color, what we are plotting here is, yeah. So if you look at here, so this is basically moment at load point. So this is going to be your failure. Okay, and this is your failure zone. Okay, what we are drawing here, and this is a inclined cracking that is going to happen because of your failure. Now, what we are telling here is depending upon how I test this beam, whether at a low ABD ratio of, let's say, 1 or 2.5 or 6, more than 6, how it is going to happen. So when the failure is happening, so for example, when it is, let's take a case of 1. Okay. Now, when I'm testing at ABD ratio of 1, the moment at which it is failing, you can see here, these are the curves. Okay. It is going to be lesser than what I'm going to have section when it is having a predominant bending action and to reach flexural capacity. So before reaching its flexural capacity, it is going to fail the moment. So the moment at which it is going to fail is going to be much lesser than when it reaches flexural capacity. So that trend, if I go to 2.5, you can see here the moment at which it is failing is going to be much lesser than that of its flexural capacity. But then when the ABD ratio starts increasing, then again the flexural behavior starts increasing. Then you see here, when higher ABD ratio, the moment at which it is failing is going to go and reach closer to that of a flexure capacity, right? So, but so when you are testing at ABD ratio of very large values of more than 6, you can see that the moment at failure is going to be higher than your flexural capacity. That means the section is going to now definitely fail in flexion. Okay, so this is basically moment at cracking and failure. Now the same thing that will happen for your uh, shear cracking also. So this what we are saying here is this is your so now we are looking at what happens to the moment at which it is going to fail for different ABD ratios. Similarly, at shear, at cracking. So let's say we can classify the beams when it is tested at ABD ratio less than 1, we call them as a very short beam. When it is tested at ABD ratio less than 2.5, we call them as, in fact, when it is less than 2.5, we call them as a deep beam behavior, where the bending action doesn't govern. It is actually governed more by the arch action, okay, the load resistance. And then when it is between 2.5 and 6.5, we call those beams as slender beams. When it is more than 6.5, we call those beams as very slender beams. Okay. So these are short beams when you have ABD ratio less than 2.5, where your arch action will start dominating. Okay. When it is between 2.5 and 6, you will have flexure and shear both will dominate the behavior. When you have more than 6, when your ABD ratio is more than 6, then the behavior is dominated by only bending action, not by shear. Of course, these are all the classification that are done by testing beams which are relatively small. And when you have shear, there is also an effect called size effect. Okay. So anyway, so you can see here in this, now if you look at this bottom figure, what we are having is, this is your lead color curve is nothing but your flexural capacity. So let's see. So this flexural capacity, what we are seeing here, is going to change, or the flexural capacity at which it is going to. These are all the beams with, as we have seen, it is with constant depth and no web shear reinforcement, and they are all tested at different ABD ratios. Okay, so these are the behavior. So you can have different failures depending upon what ABD ratio at which this particular beam is being tested. Now you see, we can also classify the modes of failures in beams, again depending upon what is the ABD ratio. So let's say if I have a beam that is tested at a ABD ratio of, let's say I'm doing a 3-point bending test, and if I'm keeping this shear span as a very large value, and if I'm keeping that ratio to be more than 5 or 6, then you are expected to have, again, we go back. F by tau is proportional to A by D. And if A by D is high, then your flexural effects are going to be high. So that is what we are saying. So the beam is going to fail in flexure. And when it is between 2.5 to 5, you will have these kind of different failure modes that are possible. Either you can have a diagonal tension failure, where your principal tensile stress can exceed the tensile strength of concrete, and you can get this kind of nice diagonal crack. Or you can have a shear tension failure. You will have this kind of crack and then flexure, but however the shear stress at the interface of the reinforcement can exceed higher than that of your bond strength, and it can lead to this kind of a splitting crack. Or you can also have diagonal compression failure, which is also called a shear compression failure. So when you test a beam at A by D ratio between 2.5 to 5, all the three modes of failure are possible. Okay. And in this location, for example, at this location, your principal compressive stress can exceed the compressive strength of concrete, and you can lead to this kind of a failure. Okay. So now, when you have a shear span to depth ratio less than 2.5, as we have said, the action will change. It's not going to be dominant by bending action. It will be more like a arch action. So the loads will get directly transferred to the support like this through formation of strut and ties. Okay, and you will have this kind of thing. So when you test a beam at a low ABD ratio of 2.5, you can have this kind of strut formation. Finally, because of this Poisson's effect, again the strut can crack in diagonal tension like this, and then you'll have this. And then if the strut also in the node region, it can also locally crush, and that we call that as a compression failure. So when you test it at ABD ratio of less than 2.5, you can have multiple failure modes. First, you generate anyway arch action, then the arch can finally fail through this diagonal cracking, or you can have a diagonal splitting failure mode, or you can have a compression failure. So all these failure modes are possible in shear. Shear is quite complex compared to that of flexure. it is not only it is function of the load, and also it's function of what kind of sectional details that are there in your section. The failure mode depends upon a lot of factors. Okay, so now if you look at it, incline cracking in RC beams, if you see here, the flexural shear crack is going to start out as a flexural crack, and then it's going to propagate as a shear crack. So, or in other words, what we are saying is it's going to initially start as a flexural crack, and then as the shear is getting more, it is going to convert itself into a shear crack of 45-degree crack. Okay, starts out as a flexural crack, and then it can. So this is what we are saying. Okay, so flexural cracks are like this. Okay, now this flexural cracks can convert itself to like this shear crack. Okay, that is what we are trying to tell. Then you can have pure diagonal tension crack. Okay, so that is what we have. So this is your pure diagonal tension crack, and you can also have this kind of a splitting failure mode. That's we said the bond failure that we have seen in the previous slide also. Now this incline cracking, what will happen is right after this cracking, what you are going to have here is that you're going to have a lot of stresses that are going to be developed across this interface, that we call that as an aggregate interlock, which we will discuss. And also you have a tension reinforcement that are connecting these two cracked elements, that is also going to contribute in dowel resistance that we will see. Okay, so for a deep beam, the crack patterns can be different. Okay, and you can see here when you are testing a beam at a ABD ratio of less than 2, we have seen that arch action will start dominating the behavior, and you form this kind of arch. You have compression strut, and then you have tension tie. Okay, now depending upon how you anchor, if the tension tie is not anchored, it can fail as an anchorage mode, or the locally that the nodes where the compression struts are joining can locally crush. So you have different types of failure modes that are possible. And when ABD ratio becomes more than 2.5, then the beam action start getting more and more dominant. In fact, more than, as we've said, when ABD ratio is more than 5 or 6, you will have a complete flexural failure. No shear failure usually happens if your design is carefully done. Okay, and so again, in when you have members that are failing in arch actions, you can have different failure modes that are possible. So for example, you can have anchorage failure of this tension tie, and you can have a flexural compression failure of this node. Then you can also have failure due to this large cracking due to flexure, and then this arch rib also can fail. So which are your this arch rib? So this arch rib can also fail. So these are different types of failure modes when the beam is acting like a deep beam, where the arch action is actually predominating the behavior. Okay, so again, see in incline crack, you can also have the shear tension failure mode, where the shear crack can actually go along the length of your rebars, which is also called as shear tension failure mode or shear compression failure mode. Okay, so this is what we said. When your principal compressive stress reaches the strength of your concrete, then you have this crushing of concrete, local crushing of concrete. So shear, in the inclined shear cracking, you have broadly, you can have either shear tension failure or a shear compression failure. Both are possible. So again, this is again, how do we classify them? You calculate your principal stresses F1 and F2. Okay, is there, let's say F1 is a principal compression, F2 is a principal tension. So if F1 becomes more than F prime T, then you're going to have tension. Okay, I'm calling this as tension. Okay, I mean, depending upon your sign convention, this is principal compression. Okay, so F2 can become more than F prime C. Then you have compression. But usually concrete is weak in tension, so this is a predominant failure mode that is possible. That is failure in shear tension. This can happen at the very end at this location because of heavy concentration of your stresses. Locally, these nodes can crush. Okay, now let's look at how the crack patterns are going to change for a continuous system. So I'm looking at one end is simple support, the other end is continuous. So if you see your bending moment diagram, and we know that the bending moment diagram is going to be negative here and positive 0 here. So you're going to have this kind of bending moment diagram, right? So that is why you have cracks, flexural cracks, which are close to this. And then wherever you have maximum bending moment, you have cracks. And the tension will be developed at this bottom location. Now, if you look at the shear diagram, again, shear diagram, we know that it is going to be like this. Going to vary like this. So that is why wherever shear is also here at this location, if you look at it, bending moment is 0, M is equal to 0, and shear is there. Okay, that's why you have nice diagonal cracking that is formed here. Okay, wherever you have maximum shear, that is going to be there. And the shear is also going to change direction, right? So that's why if you look at it here, then on this side, if you come continue, so you're going to have again shear like this, right? So again, shear force direction is going to be like this. It's going to vary like this. So shear is going to keep changing its direction. So depending upon the bending moment and shear force distribution, now you can have different types of crack patterns. Okay. In these zones, now you have both bending moment and shear are down. So you will have flexure and flexural shear crack. In these regions, you have only shear, and this is where your point of contraflexure is. So it is going to be shear dominant beam. So you can classify depending upon the bending moment and shear that is acting at the different sections. You can say that you have flexural and flexural shear region, and then you have web shear region where bending moment is 0. That is going to possibility of failing more in pure diagonal shear tension. So this is some of the beams that we have tested in our lab. So you can see here this was an I girder which was tested at A by D ratio of at about 1.5. So you have a predominant arch action. So you form the strut, and then finally the strut is formed, and then finally the strut fails by diagonal, because of the lateral tension. Okay, so you get this kind of a. This is basically a pre-stressed ultra high performance concrete eye girder, which we have tested in our lab, and you can see it was designed to fail in shear to understand how different internal resisting mechanisms are developing. So this is one of the beam. You can see a classical deep beam action, and then finally you have strut that is failing in lateral tension. Now this is again another deep beam that we tested at about A by D ratio of 1. This is, you can see, A by D ratio, I think it is about 1. And you can see clearly, when you look at the stress state, in the animation, you can see that element is subjected to compression plus shear. And when you convert it, you can convert it into principal compression and tension. So the crack direction is going to be a principal compressive direction. Okay, because crack is going to form perpendicular to tension. So it is going to follow the principal compressive stress trajectory. And this is again another beam that we have tested. You have formed this critical shear crack. So these are some of the beams with the different fibers that were tested to see what is the effect of fibers. Anyway, so this is again another beam that it was tested. Again, you can see it was tested very high A/B ratio. So shear crack, you can see that it can become quite wide. If your reinforcements are not carefully designed, it also the shear crack propagation will be much faster than your flexural crack. So now let's look at what are the different shear resisting mechanisms in beams. You have uncracked portion that is going to contribute, or in other words, the tensile strength of your uncracked concrete is going to resist your shear. And then now once the crack is formed, the crack surfaces are going to be very rough. Okay, because you're going to use, let's say, you're using a 20 mm aggregate or a 10 mm aggregate in SCC or microconcrete. So the aggregate, the crack will basically go around that aggregate. So now when these two rough surfaces are sliding against each other, you're going to generate a lot of resistance in shear. So that this phenomena we call that as aggregate interlock. Then we have a dowel action. Imagine that you have a reinforcement that is connecting these two cracked elements. Now this uh, when these two elements are trying to slide against each other, right? Now the reinforcement is not going to let these two elements slide against each other. So you're going to have generating this dowel action. So dowel action is from your reinforcement. So if you close this longitudinal bar, if you put lot of longitudinal bar, it will not let these cracked elements to slide against each other. So there's going to be the vertical component of this rebar that is going to give me resistance for shear. In addition to that, we also put a lot of shear reinforcement that is going to arrest this diagonal crack and keep the crack width very low so that all other components can contribute to load resistance. So usually what we do is internal resistance, we club all these things. Okay, we put VC, EZ is your uncracked concrete plus vertical component of your aggregate interlock plus your dowel action. All of these things are clubbed together in your code and it is given as BC. Okay, because each of them is going to vary depending upon the amount of load resistance that is going to be there. So the code is lumping everything and giving us a one simple expression in terms of BC. So this is what we have. VCZ is your the shear resistance of uncracked concrete, which is happening in the compression zone because it's uncracked. So there's going to be a tensile strength of the concrete that is available that is going to give me resistance for shear. Now VA is your this is what the aggregate interlock that we are going to generate at the interface, and the vertical component of this shear transferred across a crack is going to give me resistance, and this double action is your longitudinal bar, so that is going to connect this two cracked elements. Okay, so if I have to draw this two things, so let's say I have this kind of an element. Let's say this reinforcement is going like this. Okay, now when these two elements are going shearing, okay, this bar that is not going to let these two elements to slide against each other. So that component is what we call that as a dowel action. Okay, higher the stiffness of or higher the amount of your rebar, higher will be your dowel action. But the dowel action will start becoming less once the bar starts yielding, because once the bar starts yielding, the elastic modulus of the steel is going to reduce, and it's not going to happen. So that's what the code is saying, that each one of them will vary depending upon the amount of crack, the level of your neutral axis, and so on. So the code is saying that, okay, I'm going to lump all these things and I'm going to give you as a one simple value for your VC. Okay, that is your shear resistance of your concrete. Now each one of them will vary. Okay, that we will see it. If I start, let's say I have a beam like this, and let's say I keep applying this load. Okay, so my shear is going to be P by 2, right? If I start plotting the applied shear versus internal resisting shear, so internal resisting shear is we are plotting the y-axis, and applied shear we are plotting in the x-axis. So initially what will happen, you will keep increasing, and then you will finally you will develop some flexural crack. Okay, usually. So the first flexural crack will form. Then you also have some reinforcement that is there. Let's say some reinforcement is there, tension reinforcement is there. Okay. Now the flexural crack that forms. The moment the flexural crack is forming, then you are uncracked. So now before it cracks in flexure, everything was contribution was from your uncracked concrete. Okay, then the moment flexural crack forms, then the dowel action start kicking in, because now the crack is resisting the applied shear, right? So the dowel action will start increasing. So this is your dowel action, and then what happens, as you keep increasing more and more load, then you'll have this kind of, you'll have diagonal cracking also form. Okay, So then when you have diagonal crack that is forming, then you will have aggregate interlock between the cracked elements. Now you're going to transfer through friction and then aggregate interlock. So that will start governing. Now what will happen once your diagonal cracks are formed as well? Now I'm also, in addition to that, I'm also going to put a lot of, let's say, vertical stirrups. Okay, so that I'm going to put. So the moment inclined crack is formed, then I'm also, as the crack width is getting more and more, now I'm going to stretch this vertical stirrup. So then you'll have contribution from a vertical stirrup. Now the point what you have to keep in mind is, then the moment after, if I keep on applying the load, then the stirrup will yield. Okay, then everything, once the stirrup yields, all those resisting mechanisms will reach its maximum capacity, and then it will lead to failure. So what is to note here is the contribution of each of this component, that is this VCY, VD, VAY, VS, it is going to vary depending upon what is the level of your applied shear. So initially, if you look at it, before flexural cracking, the entire resistance was coming from your VCY. Now, if you look at right at the end, if you look at it, now you have contributions from only your stirrup and then uncracked concrete, okay, which is still, will have some level. Okay, so depending upon the level of your applied shear, internal resisting mechanism is also going to change. So that is what the code is saying, that you're doing it at ultimate. So code said, okay, I'm going to club all these things, which is basically your VCY, VD, and VAY, and it's saying that as VC in a simplified form. So VC includes uncracked concrete plus double action plus the vertical component of your aggregate interlock. All the three are lumped together and one value is given in your code. Okay, and then the stirrup will come into picture only after the incline crack, because then only the reinforcement will got activated only after the crack that happens perpendicular to that direction of your stirrup, right? So that will happen only after incline crack. So stirrup will be just sitting idle and it will be very passive. And the moment it cracks, the diagonal crack forms, then the stirrup will start governing the failure. Okay, so let's summarize what we have discussed. We have discussed the differences between shear design and flexural design, and we also discussed the relationship between flexural and shear stresses. And also we derived the formula, which is your shear formula, which is tau is equal to VQ by IB. And then we discussed what is the concept of Mohr circle. Now, why is it Mohr circle used? Because we can convert a general stress state into principal stresses, okay, which is easy for me to compare with material properties, material strength property, that what I have. Then we also discussed various failure modes, and then we also discussed what are the effect of shear span to depth ratio, and finally we discussed what are the different internal resisting shear mechanism and how it is varying with respect to applied load, right? So these are some of the references which we have taken information from, and I think the slides, most of the slides are made by my PhD student, Mr. Paleti Mohan Krishna. So I would like to thank him. So thank you. We'll continue the discussion in the next